Hey guys, welcome to 5.4 logarithmic functions. So today we're going to convert exponents to logs and vice versa. We're going to evaluate logs, find the domain of logs, graph logs, and solve logs. So anything you would ever want to do about logs. So first of all, how do we convert from an exponential equation into a logarithmic equation? Okay, so first of all, you write the word log. Now the base of the exponential becomes the base of the log, the little number below it. And the answer to a log is always the exponent. Oh, I'm sorry, this should be an A. Why did I write a 4? Okay, so the base goes there, A. The answer to a log is the exponent. So the 4 goes here. And then the 24 goes here. So when I always teach this, I call it the circle of life. A to the 4th power equals 24. It makes a big circle. All right, let's try one more. When you're converting a log to an exponential, you first write the word log. Now here's something weird. Whenever it's a base E, we're actually going to write natural log, and the symbol is ln. And there's always a secret base E anytime you use natural log. Okay, so anytime you see an E, use natural log. Again, the answer is the exponent, and then the 9 slides in right here. And if you want to check your answer, check the circle of life. E to the B power equals 9. So you know you did it right. Now, how do we go backwards? If I give you a log, can you write it as an exponential? And you would say, yes, I can. So, remember the little number is actually the base. Circle of life, the 5 is the exponent, and it's going to equal the 4. Okay, so A to the 5 equals 4. And now this one, the base is 3. The exponent is the answer here, C, and it's going to equal back to the 5. All right, so that's the conversion between the two. Now, how do we actually evaluate them without a calculator? So if anyone ever asks you to find the log of something, you're finding the exponent that gets you from this number to this number. So it's really saying 2 to what power is 16? And what's the answer? 2 to what power is 16? Wouldn't that be 4? 2 to the 4th power is 16. And part B is saying 3 to what power becomes 1 over 27? And you would hopefully say negative 3. The 3 to the 3rd is 27, and the negative just flips it. So negative 3. Okay, now solving logarithm equations. Okay, very similar. You're going to write it as an exponential. So 3 to the power of 2 equals this. Okay, so 3 to the power of 2 equals 4x minus 7, and then just solve. Okay, so 3 squared is 9. 9 equals 4x minus 7. If you add the 7 over, we get 16 equals 4x, so x would be 4. Now, one thing you guys have to check is that the base, and this we call the argument, they always have to be greater than 0. So if you ever get something that's not greater than 0 when you plug it back in, it's an extraneous solution. But this one's all good. We get a positive number, so x equals 4. Okay, B. Same thing, write it as an exponential. X to the 2nd power equals 64. X squared equals 64. What would x be? Well, you would square root both sides. Don't forget plus or minus, and you would get plus or minus 8. But what did we say? When you plug them back in, the base and the argument always have to be positive. So we actually don't want the negative answer. Your only answer is positive 8. Okay, flip it over. Graphs of logs. Turns out that the graph of a log is the inverse of the graph of an exponential. Okay, so if this is the graph of an exponential, a log graph is just a reflection over the line y equals x of that graph. So a couple crazy things here. Instead of, you know how exponentials have horizontal asymptotes? Log graphs, therefore, have vertical asymptotes. And it happens when the argument equals 0. In an exponential graph, the domain was always all reals. Therefore, in a log graph, the range is always all reals. And then the domain of a log, you just have to set the argument greater than or equal to 0. Okay, let's try one. So here's what I do for these. I start by writing it as its function without the transformations. So y equals log base 2 of x. Pretend there was no transformation. And then I'm going to write it as an exponential. 2 to the y equals x. Right? Circle of life. 2 to the y equals x. And I'm going to make a table for that. Now, a little sneaky here. Since we're doing an inverse function, we're going to actually plug in the y's as -1, 0, and 1 because the x's and y's changed. So you're going to be plugging in y's now, and you're going to be solving for x's. Okay, so 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. All right, and then let's apply any shifts. So back to our original function. If it says x plus 3, that means all the x's are getting shifted left 3. Okay, so this is now at -2.5, -2, and -1. Okay, so let's graph that. Oh, I should have gave you guys a graph. Okay, so we have, let's see, -2.5, -1, -2, comma 0, -1, comma 1. Now, some of you might be like, well, I don't know how to connect the dots. Here's another thing. The asymptote is always what you get when you set this equal to 0. So if you set x plus 3 equal to 0, that means we have a vertical asymptote at x equals -3. So at -3, I'm going to make our vertical asymptote, and that will help you sketch the log graph. It looks like a boomerang. All right, we need domain, range, and asymptote. Domain, range, asymptote. Now for this one, let's see, the domain is the set of x's such that x is greater than or equal to -3, because notice the graph is always to the right of -3. The range is always all reals for these. And the vertical asymptote is at x equals -3. So everything's switched now. This time we have vertical asymptotes instead of horizontal. All right, let's try one more graph. Okay, so again, first I like to write it without any shifts. So let's pretend it just said y equals ln of x. Let's rewrite it as an exponential. And remember, the secret base of a natural log is always e. Okay, so it would be e to the y equals x. That's our circle of life. Okay, now remember, when you make a table now, because it's an inverse function, we're actually plugging in y's. So I'm going to do negative 1, 0, 1. And we're getting x's. All right. Oh, actually, I have it up here already. E to the negative 1 was 0.3, we could just do 2 decimal places, 0.37. E to the 0 is 1, and e to the 1 is 2.72. Okay, now let's apply our transformations. In the x direction, it says x minus 2, but we know that that means we're going right 2. And if there's a negative on the outside, it's a reflection over the x-axis, which means all the y's are going to become opposite. All right, let's do it. So if we add 2 here, we're at 2.37. If we add 2 here, we're at 3, and now we're at 4.72. And all the y's are just flipping. Positive 1, 0, negative 1. All right, if you guys graph the purple, we should be in good shape. Okay, so we have 2.37 comma 1, 3 comma 0, 4.72 comma negative 1. Okay, where's that asymptote? Where's the vertical asymptote? If you set the argument equal to 0, we see that it's at x equals 2. And then you'll know how to connect the dots here. So this is an upside down boomerang because it got flipped. Okay, let's find all of our goodies here. Domain, range, vertical, asymptote. Okay, the entire graph lies to the right of 2. So the domain is all x's greater than 2. The range is always all reals because it goes up and down forever. And the vertical asymptote we said was at x equals 2. All right, awesome guys. That was everything about logs. And here is the homework. Remember, this is also due on Thursday. All right, thank you guys for watching.